We often think of stars as, well, solitary beacons, maybe sometimes with a companion or two. We've explored the fascinating dynamics of binary and even triple star systems before, right? And discovered how those relationships create these cosmic dramas all their own. What if I told you the universe is hiding even more complex, more intricate dances out there? Today, we're taking a deep dive into the truly rare and profoundly fascinating world of quadruple star systems. We've pulled together a stack of intriguing sources to understand these cosmic configurations. We're going to try and untangle what they are, how they're arranged, the incredible challenges of observing them, how they evolve, and maybe most importantly, we'll uncover the surprising insights they offer into fundamental astrophysical processes, especially, through the lens of recent research and the transformative data from the Gaia mission. Okay, let's unpack this cosmic ballet.
Yeah, our mission here is really to get a good handle on these complex stellar families. We'll explore what makes them tick, how they form, and why they're actually so crucial to our understanding of the universe. Get ready to appreciate the intricate beauty of these cosmic ballets happening out there in the vastness of space. It's pretty amazing stuff.
So let's step onto the cosmic dance floor. First off, just how rare are these quadruple star systems? You might think more stars must be more common, but nope. Imagine a grand ballroom. Most dancers are soloists, maybe pairs. A study back in 2014 looking at sun-like stars pretty close by found only about 4% were quadruples, just 4%.
Yeah.
Compare that to like 54% single stars and 33% binary systems. That immediately sets the stage. These intricate setups are really, really uncommon.
It truly does. And when we talk about four stars, it's not just, four random individuals flinging around each other chaotically. The universe, in its surprising order, tends to arrange them into two main stable configurations. These were wonderfully illustrated way back in 1968 using what they called mobile diagrams. Think of them as very specific choreographies for this four-star dance.
Okay, specific choreographies, what are they?
So the first is called Hierarchy 2. Imagine two separate binary systems, right? Each with its own pair of dancing stars. Then these two pairs are dancing around a common center, orbiting each other.
Ah, okay. Like two couples on the dance floor circling one another. Got it.
Exactly. Then the second stable configuration is Hierarchy 3. Here you have a tight triple star system, a trio dancing together, and then a fourth single star is orbiting that entire triple system.
Right, like a dance trio with a solo partner circling way outside them.
Precisely. So the key insight here isn't just that there are four stars, but that they arrange themselves in these very specific, stable dance patterns. It's kind of a testament to the universe's surprising order amidst, well, potential chaos. And I should mention there are also unstable, short-lived things called trapezium systems you find in star-forming regions. But these two hierarchies are the stable, long-term players we focus on.
And what's really compelling, even though they're organized like this, observing them sounds like a nightmare. It's that great range of geometries, separations, and mass and magnitude differences you mentioned that makes getting a complete survey so incredibly difficult. Think of it this way. Measuring a single star is like tracking one person on a dance floor, relatively straightforward, right?
Sure, yeah.
But a quadruple system, it's like tracking four dancers, each doing their own thing while they're paired up and the pairs are orbiting each other. It just demands vastly more data and, crucially, more time to map out their full 3D choreography.
Exactly right. For a mission like Gaia, measuring a single star involves, maybe 5 or 6 parameters, position, motion, distance. You can often nail that down in just 3 or 4 years. But for multiple systems, you need many, many more observations. And this is key, a much more extended temporal baseline.
More time.
Yeah, because the observation time you need critically depends on the orbital periods of all the components involved. Those inner binaries, for instance, they could be spectroscopic, meaning we only detect their wobble through light shifts.
Okay.
Or they might be eclipsing, where one passes in front of the other, causing a dip in brightness.
Right.
Or, if you're lucky, they might be fully resolved, meaning you can actually see the individual stars as separate points of light. And then those binary pairs themselves can be incredibly compact, orbiting super fast, or they could be in such wide orbits that they're almost unbound, taking centuries or millennia. So yeah, this raises that important question. How exactly do scientists even begin to untangle such a complex gravitational ballet?
That's the core challenge, absolutely. And it's truly remarkable what scientists have managed to uncover despite that. Let's look at some snapshots from the cosmic dance floor, make this a bit more real. Among the known quadruple systems, you might actually be surprised to hear some familiar names, like Capella, for instance. Turns out it's a pair of giant stars orbited by a pair of red dwarfs. 4 stars.
A classic example.
Then there's Mizar, in the Big Dipper's handle. Looks like a visual binary through a small telescope, right?
Yeah.
But each of those resolved components is itself a binary. So boom, 4 stars again.
Exactly, a binary of binaries.
And what about Kepler-64? That one's famous, isn't it? Hosting the first exoplanet found in a quadruple system.
That's the one, PH1b, orbiting 2 of the stars in that 4-star setup. Incredible.
Just imagine the sunsets there. Anyway, we also have others like HD 98800, a young nearby system, 2 spectroscopic binaries, and one even has this gas-rich disk around it, oriented polon.
Yeah, a fascinating system. And there are others, VWLMI, Tau, GJ867, each with its own unique story.
So these aren't just theoretical ideas, they're out there doing their intricate thing.
It's truly astonishing to see them, yeah. And that naturally brings us to the how do these incredibly complex multiple star systems even form in the first place? It's a field with, well, many complexities. We're especially looking to Gaia's data now to constrain the shapes of their orbits, the eccentricities, which really helps distinguish between different formation hypotheses.
Okay, so what are the main ideas?
Well, currently, there are 2 main mechanisms on the table. The first is fragmentation. This can happen early on, like turbulent fragmentation during the initial chaotic collapse of a giant gas cloud. Or it can happen a bit later, called disk fragmentation, where a rotating disk of gas and dust around a young star breaks apart due to instabilities.
Okay, fragmentation. What's the other one?
The second mechanism is capture. Here you have initially unbound stars, just wandering through space, that manage to gravitationally snag each other and form a bound system. This usually requires shedding some energy, maybe by flinging away a third star, or through interactions with gas disks around the stars.
So they either break apart from the start, or they grab partners later on.
That's the basic idea. Interestingly, an older idea called fission, where a single star spins up so fast it breaks into 2, is now largely disfavored for making binaries. But what's fascinating here is that even with these main mechanisms, the story gets more complicated. You've got things like ongoing gas accretion feeding the stars, dynamic interactions between the stars and their surrounding disks, interactions within higher multiplicity systems themselves as they settle down, and even tidal forces stretching and pulling on the closest binary pairs. All these factors play a role in shaping the final configuration.
Wow.
So the key insight is, stars aren't just born solitary. They often fragment or capture companions, leading to these incredibly complex family trees right from the very beginning.
That is a lot of variables right from the start. And then, okay, once these systems form, they don't just sit there in a fixed pattern, do they? You mentioned they dynamically evolve over time, constantly influenced by gravity in ways that go beyond simple orbits, this gravitational tango idea.
It truly is a tango, a very long, slow tango, mind you. Even before Gaia, statistical studies hinted at this complexity. There was a study, I think back in 2008, comparing lots of binary quadruples with triple systems. And they found interesting patterns, like the inner pairs, the really tight orbits in both triples and quadruples. They looked pretty similar in terms of their periods. But the outer orbits, the wider separations, and the mass distributions, they were quite distinct between triples and quadruples.
So different dynamics depending on the scale.
Exactly. It suggests different evolutionary paths or dominant influences depending on how the system is structured. And this leads us directly to a really curious and frankly quite weird gravitational phenomenon called the Kozai-Lidov resonance, or sometimes Lidov-Kozai.
Kozai-Lidov. Okay, sounds complex. What is it?
Imagine an inner binary system, 2 stars orbiting each other relatively closely. Now add a third star orbiting much, much further out. Over very long timescales, much longer than the inner binary's own orbital period, that distant third star gravitationally perturbs the inner binary's orbit. It causes this periodic exchange between the inner orbit's eccentricity, how stretched out it is, and its inclination, how tilted it is relative to the outer star's orbit.
So the distant star slowly makes the inner pair's orbit wobble and stretch.
Precisely. It can drive the inner orbit to extremely high eccentricity, making it incredibly elongated, almost like a comet's path, and it can even flip a moderately inclined orbit. Imagine it orbiting clockwise relative to the outer star. This effect can actually flip it to orbit counterclockwise or retrograde.
Whoa, that's a mind-bending concept. A subtle gravitational nudge building up over millennia to completely change the dance.
So what's the most dramatic consequence we see from this in quadruple systems specifically? You've got it perfectly. Now, take that Kozai-Lidov idea and apply it to a quadruple system, specifically the hierarchy 2 type 2 binaries orbiting each other. In this setup, each binary can act as a Kozai-Lidov perturber on the other binary.
Oh, okay. They perturb each other.
Right, so both inner binaries can experience these significant oscillations in their eccentricity. They can be driven to very high values. Studies suggest maybe 30 to 50% of these inner binaries in quadruples might reach an eccentricity greater than zero point 0.3, which is quite significant. And yes, orbital flips and even collisions between stars in the inner binaries are also enhanced in quadruples compared to triples. It's even been suggested that some triple systems might actually be the remnants of quadruple systems where one star got ejected or collided.
So quadruples might even make triples sometimes.
It's a possibility being explored. If we connect this to the bigger picture, it just shows how incredibly subtle yet powerful gravity can be on cosmic timescales. It's shaping the evolution of entire systems in ways we're only just beginning to fully grasp. It's gravity's long game playing out, you know?
That's a perfect segue, because given these huge observational challenges and the sheer complexity, you might be wondering, how is Gaia helping us unravel all this? If figuring out these 3D orbits is so tough, how are we actually making progress?
Gaia is, well, it's nothing short of revolutionary in this area. It's contributing massively both by discovering more of these systems and by helping characterize their orbits with just unprecedented precision. That high accuracy astrometry is key. For instance, there was work by Tokovinin in 2022 using Gaia's early data release, focusing on stars within about 100 parsecs our galactic neighborhood. From that huge data set, he identified nearly 400 hierarchical triple systems, which is already a lot. But alongside those, he found 30 definite quadruples and even one quintuple system, Alpha Scorpii.
Wow, 5 stars bound together.
Yeah. Antares A and B plus companions. And then another fascinating example, also from 2022, by Fazenko and colleagues. They specifically searched the Gaia data for co-moving pairs, stars moving together through space, where both components were also known eclipsing binaries. So looking for 2+2 systems directly.
Okay, a very specific search.
Very specific. And what they found was quite striking. They uncovered 8 new 2+2 systems. These had very short inner periods, less than half a day, but surprisingly wide outer separations, like over 1,000 astronomical units. But here's the kicker. Finding 8 was 7 times more than what you'd expect just from random pairings of eclipsing binaries.
7 times more. What does that imply?
It strongly suggests that the presence of that wide companion somehow enhances the formation or survival mechanism of the short period binaries. Maybe the wide companion helps funnel material in early on, or maybe it stabilizes things. We're still figuring it out, but it's a clear statistical signal.
It's like the outer pair influences the inner pair's formation. Cosmic matchmaking, maybe?
Maybe something like that. And, these are just 2 examples. A number of other studies are mining this Gaia data right now, looking for multiples in different ways.
And what's really compelling, I think, is that all this discovery isn't just about cataloging stars, right? It's about what these systems tell us. These multi-star systems, especially quadruples, are giving us these incredible insights into some really fundamental processes in astrophysics.
Let's talk about 2 specific, really illuminating examples that come directly from Gaia's work on quadruples.
Absolutely. Let's do it. For our first application, let's look at type Ia supernovae progenitors. These are the standard candle explosions vital for cosmology. Now, for a long time, simulations have struggled to explain how often we actually see these supernovae. The leading theories involve either white dwarfs colliding in dense clusters, or maybe 2 white dwarfs in a binary system merging. People looked at Kozai-Lidov effects in triple systems to see if that could push white dwarfs together often enough. Turns out, probably not. The rates were too low.
Okay, so triples weren't enough to explain the observed supernovae rate. Right. But what's fascinating here is that Kozai-Lidov oscillations in compact quadruple systems might actually be a key part of the solution. There was a study in 2022 focusing on a specific system, HD 744384. It's young, relatively nearby in an open cluster, and it's a short period spectroscopic 2+2 quadruple.
A perfect test case.
Exactly. It has an outer orbit of about 6 years, moderately eccentric, and 2 inner binary orbits, one around 20 days, the other just 4.4 days. Also eccentric. And crucially, the orbital planes are not aligned. They're tilted relative to each other.
The tilt is important for Kozai-Lidov.
Precisely. By combining ground-based observations with Gaia's super-accurate astrometry over time, they showed this system is undergoing these long-term secular gravitational interactions. And these interactions seem to have pumped up the eccentricity of one of the inner orbits way higher than you'd normally expect for stars of that type and age. Now, the crucial part, they modeled its future dynamical evolution, and their conclusion, HD 74438 is an excellent candidate progenitor for producing a type Ia supernova specifically,
Ah,
a sub-Chandrasekhar type, through the eventual merger of the two white dwarfs that will form in one of those inner binaries.
Wow. So a quadruple system could directly lead to a standard candle supernova.
It seems very likely in this case. Which, of course, raises the important question, just how common are systems like HD 74438? Could they be a significant missing piece in the type Ia supernova puzzle? It's a really exciting connection.
That is fascinating. Okay, what's the second application?
For the second one, we pivot to something seemingly quite different: white dwarf crystallization. Now, we've talked before about how Gaia data provided evidence that white dwarfs, the dense cores left behind by stars like our sun, actually crystallize as they cool down over billions of years. You can see a sort of pile up in their distribution on diagrams.
Right, the cooling slows down when they crystallize, releasing latent heat.
Exactly. But later theoretical work found that the cooling delay needed to match the Gaia observations was actually larger than the simplest models predicted. It suggested there might be additional energy sources or processes happening inside these cooling white dwarfs.
Okay, so a slight mismatch between theory and observation.
A slight, but important one. Now, enter a recent Gaia discovery from 2023. Researchers identified a white dwarf called HD 120420c. It's really close, just 32 parsecs away. And what's special is that Gaia's data showed this white dwarf is gravitationally bound to a known triple star system, HD 19042. So the whole thing is actually a quadruple system, like Sirius, but with a triple primary instead of a single star.
Okay, a white dwarf found orbiting a triple. Why is that significant?
Because if we connect this to the bigger picture, its position on the temperature mass diagram tells us it's right in the zone where white dwarfs should be undergoing crystallization. This makes it the first confirmed crystallizing white dwarf whose total age can be externally constrained from the properties of its bound companions.
Ah, because we can figure out the age of the triple system stars, and the white dwarf must be the same age.
Exactly. We get an independent age check. Now, with the current data, the age measurement for this specific system isn't quite precise enough to strongly distinguish between different detailed models of crystallization and extra energy release. Like, there's this idea involving the element neon settling out called 22Ne phase separation. The results are compatible with that idea, but not definitive yet.
But the potential is there.
The potential is huge. The study inferred that similar systems, white dwarfs orbiting nearby, age-datable multiple systems, are likely common. So as future Gaia data releases give us even better measurements, we should be able to find more systems like this and perform much more stringent tests of our models for how white dwarfs cool and crystallize. These hidden cosmic dances are literally illuminating the fundamental physics happening inside dead stars. It's pretty incredible.
so what does this all mean then? We've taken this journey from understanding just how rare and frankly complicated these quadruple star systems are, to the intricate ways they arrange themselves, the huge challenges in just seeing them properly, and the profound impact of these subtle gravitational effects like Kozai Lidov resonance. And all of this understanding is being absolutely transformed by the unprecedented data pouring in from the Gaia mission. It seems really clear now that these complex multiple star systems, especially quadruples, they aren't just, astronomical curiosities. They're vital for understanding really fundamental cosmic processes, everything from the mysterious origins of supernovae to the very internal workings of dying stars.
Yeah, it absolutely reinforces that idea that these systems are like unique cosmic laboratories. They provide these extreme dynamic conditions that we just can't replicate here on Earth. They let us test our theories about star formation, about the subtle long-term effects of gravity, and about the ultimate fates of stars. It's those aha moments, isn't it? Like realizing how this intricate gravitational dance can lead to something as spectacular as a type Ia supernova,
Yeah.
or something as subtle and fundamental as figuring out exactly how a white dwarf cools and solidifies over billions of years. That's what makes this field so captivating.
It really does. It just makes you wonder what else is hiding out there, performing its own silent millennia-long dance that we're only just beginning to tune into. Think about how much more there might be to discover in those seemingly empty spaces between the stars we see. The universe is apparently full of these intricate hidden dances, constantly shaping galaxies, determining the fates of entire stars. What other secrets might these multi-star systems be hiding? Something to ponder. Keep exploring, everyone, and stay curious about the cosmos.